Redistributions of neutrinos. By hypothesis, the elementary particles redistribute the types and the velocities of the neutrinos that collide with them. As has been said, the model distinguishes two types of matter, p-type and n-type matter. Parallelly, there are two types of neutrinos, p-type and n-type neutrinos, but neutrinos are not particles made of matter. When a neutrino collides with a particle of matter of the same type to that of the neutrino gives impulse to the particle and hence increments its velocity, and the neutrino bounces back. This type of interactions between a neutrino and the particle are called impulse or impulsion interactions. When a neutrino collides with a particle of matter of the opposite type to that of the neutrino switches its type and continues with its previous velocity. In these interactions, the collided particle does not suffer an impulse. This type of interactions, neutrino-particle, are called switch interactions. Impulsion interactions. The elementary impulse given to a material particle in a collision with a neutrino of the same type to that of the particle is defined as the product of the velocity of the neutrino relative to the particle by a universal constant that will be called h sub 1. It is convenient to suppose that when a neutrino falls on a particle of its same type, the collision is not always effective, but the probability that an impulsion interaction is completed depends on the speed of the neutrino relative to the particle. It will be supposed in what follows that such probability or cross-section of an impulsion interaction is the function shown in expression number 2, where v sub r is the speed of the neutrino relative to the particle. A sub I is a constant specific of the particle, and b sub I is a constant common to most elementary particles. As was said earlier, when a particle receives an impulsion from a neutrino of velocity v sub r relative to the particle suffers an increment in its velocity that is proportional to the relative velocity of the neutrino and inversely proportional to a constant mu sub p specific of the collided particle. The constant mu sub p specific of the particle is identified by the model as its inertial mass. The impulsion interactions have no influence on the redistribution of neutrinos created by a particle, since they neither change the type nor the velocity distribution of the incident neutrinos, because having supposed that the impulsion neutrinos reverse their velocity at the interactions, those neutrinos removed by the bounce backs from the flow incident on the particle along a given semi-direction are replaced by those neutrinos added to such semi-direction at the bounce backs of the other side of the particle. Switch interactions. When a p-type neutrino collides with an n-type particle of matter, or when an n-type neutrino collides with a p-type particle of matter, the neutrino swaps its type from p to n or vice versa. These type switches imply that the material particle creates a redistribution of neutrinos, since it emerges from it a different distribution of neutrinos to that incident on it. By the moment, it will be supposed that those neutrinos that suffer a switch interaction emerge from the particle with the same velocity that they had before the interaction. It seems again adequate to suppose that when a neutrino falls on a particle of the opposite type, the interaction is not always effective, but the probability that a switch interaction actually takes place depends on the speed of the neutrino relative to the particle. It will be supposed in what follows that such probability or cross-section of a switch interaction is again a function like the one shown in expression number 4, where v sub r is the speed of the neutrino relative to the particle. A sub s is a constant specific of the particle, and b sub s is a constant common to most elementary particles. The sub-index s has been chosen to remind that it concerns a switch interaction. Notice that both the switch cross-section and the impulsion cross-section are by hypothesis described by the same function. It will be supposed that in the reference frame of the ether at rest, the speed distribution of neutrinos of an ether not disturbed by near matter is of the Maxwell-Boltzmann type. That distribution can be written as shown in the equation number 5, where v is the speed of the pertinent neutrinos. N sub 0 is the total number of neutrinos of both types by unit volume. It is supposed that in our local region of the universe, the abundance of neutrinos p and n is approximately the same. V sub m is the speed for which there is a maximum of neutrinos. V sub m is believed to be at least thousands of times the speed of light. The distribution given in the equation number 5 will be called canonical distribution of the ether. With those hypotheses about the cross-sections of a particle and the distribution of neutrinos in an undisturbed ether, it is straightforward to calculate the redistribution of neutrinos created by a particle due to its switch interactions with the neutrinos when the particle is bathed by a canonical ether in which the particle is at rest. By redistribution of a particle, it must be understood the excess or the deficit of neutrinos of a given speed relative to the particle that emerge from the particle by unit time and by unit solid angle. The excess or the deficit are in relation to the number of neutrinos of the corresponding speed that would emerge the space assignable to the particle if the particle was not there. The number of neutrinos of the opposite type to that of the particle, of speed v relative to the particle, that suffer with it switch collisions by unit time and by unit solid angle is given in equation 6. And since those neutrinos disappear in the collisions because they change their type, the redistribution of neutrinos of the opposite type to that of the particle is given in equation 7. But on the other hand, since those neutrinos that disappear are transformed into neutrinos of the opposite type, though with the same speed, the particle creates an excess of neutrinos of its type, and therefore the redistribution of neutrinos of the same type of the particle is the one given in equation 7b, whose plot is shown in figure 7b. Redistribution due to a particle that moves relative to the ether. When a particle moves relative to the ether, it will no longer receive by all directions the same flux of neutrinos, and therefore it can no longer be expected that its redistribution is isotropous. But it has been observed with computer simulations that supposing a particle that moves through the ether at 4 times the speed of light, and supposing an ether in which the speed for which it has a maximum number of neutrinos is as small as 30 times the speed of light, it happens that the redistributions that emerge by different directions of the particle differ by less than a 2% from the redistribution corresponding to a particle at rest in the ether. If the distribution of the surrounding ether is instead supposed to have a maximum number of neutrinos for a speed much bigger than 30 times the speed of light, then the directional redistributions created by a particle moving at 4 times the speed of light became undistinguishable for the computer program. This approximate invariance of the theoretical redistributions allows the model to guarantee the stability of atoms and molecules when they move at high speeds relative to the ether. Furthermore, such invariance of the redistributions, together with the fact that the force that a particle exerts on another particle depends only on the velocity of this particle relative to the first, implies an invariance of the forces between particles. Force between two particles moving relative to one another. Consider first the special case in which a particle B moves directly away with a velocity u from another particle A. The reference frame of description for the neutrino speeds v, for the speed u of the particle B, etc., will be the one associated with the particle A, that will be supposed to be at rest in the ether. The force that has been defined as the sum of the elementary etherical impulses in unit time suffered by the particle B due to the excess or deficit of etherinos created by A acts by symmetry along the direction AB, and its modulus is given in the equation number 8, where d is the distance of B from A at the instant of evaluation of the force. R sub A is the redistribution of etherinos created by the particle A. Sigma sub IB is the cross-section of the particle B to its impulsion etherinos of speed v sub r relative to it, and where the speed v sub r relative to B of an neutrino whose speed in the reference frame of description is v is given in equation 9. The force given in equation 8 exerted by A on B has been evaluated with numerical integrations for a wide sample of speeds u of the particle B. The plot of this force is shown in figure 8, where the values of the force for negative values of the speed u correspond to the particle B approaching A. It has been observed that the speed u for which the force changes its sign, becoming an attraction force, does not depend on the value of the speed for which the canonical distribution of the ether has a maximum number of etherinos. The constants B sub s and B sub I of the cross-sections have both been assigned ad hoc the value 1.255 divided by the square of the speed of light, so that the force is 0 when the speed u of the particle B equals the speed of light, which is considered of interest for the model as will later be explained. The force becomes negative, meaning attraction, when the particle B moves away from A at speeds bigger than the speed of light, because in this scenario the particle B is catching from behind many slow etherinos departed earlier from A. Consider now the case of a particle B that in the instant of evaluation of the force is moving perpendicularly to the straight line AB joining both particles with a velocity u. The reference frame of description will again be the one associated with the particle A. Now the force that A exerts on B can be decomposed in two components, one in the direction AB and the other in the direction perpendicular to AB, which is the direction of the velocity u at that instant. The values of those components are given respectively in the equations 10 and 11. But where a neutrino whose speed is v in the frame of description has now the speed v sub r relative to the particle b given in equation number 12. The component along AB and hence perpendicular to u of the force exerted by A on the target particle B, see equation number 10, has been evaluated with numerical integrations for a sample of values of the speed u. The plot of this force is shown in figure number 10. Anisotropous redistributions. There are many facts about the elementary particles, like for instance their magnetic moment and spin, that suggest that the majority of them, for example the electron, the proton, neutron, and their antiparticles, have an internal anisotropic structure. The model will try to describe the behavior of these particles, assigning them anisotropous redistributions. That is, redistributions that depend on the direction by which emerge the heterogeneous relative to some internal direction of the elementary particle. To implement these anisotropous redistributions, it will be supposed that the switch cross-sections of those particles depend on the direction of incidence of the heterogeneous relative to the particle, by simply making the constant A sub s of the cross-sections depend on such direction. To illustrate the description, some examples of possible anisotropous redistributions are now shown, but they must not be considered final proposals of the model. Proton. Suppose that the proton has an axial symmetry both in its internal structure and in its redistribution of heterogeneous. The symmetry axis of the particle, in this case of the proton, will be called its PRA, or preferred redistribution axis. Suppose that the redistribution of the proton is characterized by being stronger the greater is the latitude angle alpha that the velocity of the incident and hence emergent heterogeneous make with the equatorial plane of the proton. It is being assumed that the proton is a p-type material particle that transforms n-type heterogeneous into p-type ones, and it will be supposed that its redistribution increases with the latitude angle alpha. The directional redistribution of the proton will be implemented supposing that the constant A sub s that characterizes the proton's cross-section to switch interaction increases with the latitude, for example, as shown in the expression number 14. And therefore, the switch cross-section of the proton would be as shown in the expression number 15. A symbolic image of the proton could be the following blue sphere, where the redistribution of heterogeneous would be maximum at its poles, darker blue, and would decrease gradually to zero towards the equator. Along the equatorial directions of the proton, the redistribution of heterogeneous would be negligible, and hence two protons in proximity with their PRA aligned perpendicularly to the straight line joining them would not repel. The following picture, figure 11, sketches a few heterogeneous incident left image and later emergent right image of a proton with the proposed axial symmetry. Electron. Suppose that the electron also has an axial symmetry both in its internal structure and in its heterogeneous redistribution. Its symmetry axis will be called the electron's PRA. The electron is assumed to be a type N material particle that transforms p-type heterogeneous into n-type ones, but again with the probability that would depend on the angle alpha that the velocity of the incident neutrino makes with the equatorial plane of the electron. But unlike the proton, it seems adequate to suppose, due to reasons related with other phenomena, that for the electron the strength of its redistribution decreases when the latitude angle alpha of the direction being considered is increased. Such behavior could be implemented supposing that the constant A sub s that characterizes the electron's switch cross-section now decreases with the latitude alpha, for example, as shown in the expression 16. And therefore the switch cross-section of the electron would be the expression 17. This is only an example and not the final proposal of the model. A symbolic image of the electron could be the following red sphere, where the redistribution of neutrinos would now be minimum at its poles in lighter red and would increase gradually towards the equator. Neutron. The model considers that the neutron is a bound system made by a proton and an electron. It seems plausible that in the neutron the electron orbits the proton in a similar way to that in which an orbital electron orbits the proton in the hydrogen atom. But in the case of the neutron, the proton's PRA would maintain in relation to the electron's PRA a different and special alignment. In any case, if it is supposed that in a neutron an electron orbits a proton, this implies that the neutron can also be considered a particle with an internal structure with axial symmetry, whose symmetry axis, that is the neutron's PRA, will be perpendicular to the orbital plane of the electron. If the neutron was an association of a proton and an orbiting electron with their PRA aligned in parallel, like in figure number 12, then such neutron, when observed from outside locations at small angles from the neutron's PRA, would appear as a p-type particle of positive charge, since from those locations the proton's redistribution, which is strong at directions close to its PRA, dominates over the electron's redistribution, which is weak along its PRA. But when the neutron is instead observed from outside locations at small angles from its equatorial plane, it would appear as an n-type particle of negative charge, since from these locations the electron's redistribution dominates over that of the proton. The alignment of their PRA shown in figure number 12 is not the only one that, according to the model, allows for a stable orbit of an electron around the proton. It is just an example that suggests that two neighbor neutrons can attract themselves when their PRA have some adequate alignments. In this example, when the PRA of a neutron points to the equator of the other. This is the paradigm with which the model aims to explain the strong force between nucleons. The following picture number 12 sketches the redistribution of a few neutrinos incident in the left image and later emergent in the right image from a schematic neutron with the proposed axial symmetry. Force between two elementary particles at rest and Newton's third law. It will here be described the case of two equal particles that are at rest relative to one another, but it will be easy to generalize the results for two different particles. The force that, according to the model, the particle A exerts on the particle B is shown in equation number 18. Where the redistribution of neutrinos R sub A created by A has been replaced by its value. Similarly, the force exerted by the particle B on the particle A is shown in equation number 19. Since it has been supposed that the particles A and B are equal, it is evident that the switch cross-section of A is equal to the switch cross-section of B, and that the impulsion cross-section of A is equal to the impulsion cross-section of B. And there would be so far no objection to suppose that the switch cross-sections of these particles are different, for example stronger, than their impulsion cross-sections, because in this case of two equal particles, it will still happen that their mutual forces are equal and opposite, and therefore Newton's third law, action equals reaction, would be preserved. That is so because notice that in this case in which A and B are equal particles, the integrands of their mutual forces both contain the product of the switch cross-section of the first particle by the impulsion cross-section of the target particle. And those products are equal in both integrands due to the equalities 20 and 21. But consider now the case in which the A and B are different particles, and suppose for example that A creates a stronger distribution of heterogeneous because of having a big switch cross-section, but instead A is weakly sensible to its impulsion heterogeneous because of having a small impulsion cross-section. And suppose at the same time that with the particle B the opposite is true. Then the product of cross-sections that enters into the integrand of the force that A exerts on B would be greater than the product of cross-sections that enters into the integrand of the force that B exerts on A, leading to the result that the former force would be greater than the latter, and hence contradicting Newton's third law. To avoid such inadequate prediction, the model adopts the following hypothesis. For every ordinary elementary particle, its switch cross-section is, by hypothesis, equal to its impulsion cross-section. With that hypothesis, in the previous case in which the particles A and B are different and at rest, their mutual forces will now be equal, since the products of two cross-sections appearing in their integrands can be rewritten by the same expression. In the case of anisotropous particles with an axis of symmetry, their cross-sections will depend not only on the relative speed of the heterogeneous, but also on the angle alpha that their velocity makes with the equatorial plane of the particle. And the previous hypothesis will be generalized as follows. By hypothesis, for every ordinary elementary particle with axial symmetry, the directional switch cross-section of the particle is, for every direction of the heterogeneous, equal to its directional impulsion cross-section. Notice that in the case of two particles A and B at rest, and whose PRA don't rotate, the angle alpha sub A that the velocity of an heterogeneous emerging from A with semi-direction AB makes with A's equator is equal to the angle that the velocity of an heterogeneous coming from B with semi-direction BA makes with A's equator. And the same is true for the particle B and its angle alpha sub B.